Hi class, today we're going to be discussing behavior of real gases. This is the last section in chapter 7. So basically, an ideal gas does not exist. Ideal gas law describes the behavior of real gases quite well at low pressures and moderate temps, but not at high pressures and low temps. So if we take a look at this chart here, we can see PV equals RT, which is equivalent to 1. So an ideal gas, so 1 mole of an ideal gas equals 1 for all the gases. And that's what this dotted line means. But as you can see, that's not what's actually happening here. So as the pressure increases, the deviation for the real gases is quite large and different from each gas. So none of them behave the same way either. They're quite different from each other. So what does this mean? This means that real gases do not behave ideally at high pressure, which conflicts with the postulate that we've covered in the kinetic molecular theory. So postulate 1 states that the volume of spaces occupied by molecules is negligible compared with the total gas volume. That works under low pressure. There's a lot of volume here, which means there's a lot of space in between each molecule. So the chance of their colliding with each other is lower than something that has high pressure. So at low pressure, perfectly fine, that works. But at high pressure, which is what we see here, so now it's compressed, the volume is not as much as it was here, so the space is limited in between the molecules. This becomes important. So the volume of individual molecules becomes important. The space through which a molecule can move is significantly different from low pressure. So they're going to interact more, causing more collisions with each other and against the wall. And we cannot compress it we cannot ignore that it's negligible anymore. The volume of the gas does exist when it's in certain conditions such as high pressure, where it's been condensed, and the volume is very limited. Postulate 3 states that the forces, we're going to take a look at this one over here, states the forces of attractions between molecules in a gas are very weak or negligible. So basically they have elastic collisions. Think of balls on a pool table. They will bump into each other, and if there's enough force, they'll keep going. So here is what ideal gas law. They will collide with each other, but they will keep going as elastic. The kinetic energy is never lost. And with real gases, that doesn't happen. As you can see, this is a large arrow, this is a smaller arrow. The molecules do interact with each other. There is intermolecular forces occurring between them. So these are forces of attraction in a gas do occur. So this approximation is very good at low pressures where the molecules tend to be far apart, A. But B, intermolecular forces become significant at higher pressures because molecules tend to be closer together. So what ends up happening is that over here, the pressure is actually lower than the predicted ideal gas behavior. As a molecule, so let's look at this red molecule here, begins to collide with the wall surface, neighboring molecules pull this colliding molecule slightly away from the wall, giving a reduced pressure. So the pressure is actually lower than what we would calculate with the ideal gas law. So now we get into corrections for the non-ideal behavior. So this is where van der Waals comes in. Van der Waals was a Dutch physicist who was the first to account for these deviations. I didn't put it down because I'm not going to ask you about that. But I will and could ask about van der Waals equation. So the van der Waals equation is similar to the ideal gas law, even if it doesn't look like it right here. It might look a little crazy, but it includes constants A and B, and they account for the deviations from the ideal behavior. So if we look at ideal gas law, which is PV equals nRT, the ideal gas V now becomes V minus NB. And P now becomes this P plus N squared A over V2. So this is where the adjustments would be. And these constants, you would be given a table. They are specific for each gas. So they're not just random numbers. You wouldn't have to calculate that portion. They would be given to you. So and I'm going to do a couple problems so you can see. Here is van der Waals gas constants for molecules. So you would look here and it would be given to you in order to calculate with this information. So A has to do with pressure, B has to accommodate with the volume, and both are used to because of the deviations from the real behavior, real gas behavior. So here's a problem. Calculate the pressure of 95 grams of NO2 gas at 11.2 liters and 400 K using A, the ideal gas law, which everybody should know, and then B, the van der Waals equation. I, of course, picked the gas that is not on here, but had it been on here, you would simply go across, write down A, write down B, and then plug it in. So let's do the ideal gas law. Here it is. I thought I had written the A's here, but somewhere I think I deleted. I had put A and B. Oh, I put it for the second one. So PV equals nRT. Here is the 95 grams of NO2, but we get the moles out of this. We have our R constant, the temperature in Kelvin, and our volume, and it gives us 6.05. Based on the information that I discussed regarding the molecules here, if the molecules are actually attracted slightly to the other molecule that's going to collide, then the pressure will not be as much as what's been calculated in ideal gas law. So we anticipate, if we did this right, a lower a value than what you see here. So I gave you the constants to allow you to, since they weren't on the chart, so I couldn't pull them out. And then we rearranged the van der Waals equation. So we are trying to figure out the difference between using the ideal gas law equation for pressure, and now we're going to use the van der Waals with the constants because of the deviation in behavior of a real gas. So once this has all been, it looks kind of crazy, but a lot of it is still the same. We have our mole, we have our R, we have our T, and then we have the volume, and then our constant with, so N equals moles. So we would take it again, and then we would have B, the constant for B, which is right here. And then you would subtract A, which is the constant that's here. And then we would just follow it again, N squared over the volume, which we have all that information. So it looks like a very big, difficult equation. You guys have handled far worse than this. And you survived chapter 6. So believe me, this is nothing. And it ends up having a pressure, all the units should cancel out, of 5.92. This is definitely lower than 6.05. Not a lot, but it is lower, and it did take into account the deviations for it. So you see, I did 2 different equations, one with ideal gas, one with van der Waals, and you can see the difference between them. Okay, and that is it. Thank you.